Right, this should be working now. Just let me know if the sound is good, if everyone can hear me correctly, and otherwise, good morning, good afternoon, wherever you are. So yeah, can people hear me correctly? Is it loud enough? Perfect, thanks, yep, great. So today I wanted to work on a small PR on Julia itself, which I've not done that much, or not done at all, I mean not major contributions. I started working on some specific, a bit noisy in the background, interesting. I'm not sure what might be noisy, it might be, it might be saturating a bit. Should I reduce the sound? It's weird because I should not have any sound in the background. Interesting. Well, let me mute myself and listen to the stream. Okay, I hope the fan noise, yeah, it might be okay. This is definitely the fan noise from the laptop. Trying to manage streaming and surviving at the same time, and we're not yet compiling anything in Julia, so that would be fun. Right, yeah, it might be the fan, but I don't think I can do much about it. Maybe try to step away. Okay, yeah, if it's manageable, okay. Because one of my streams, I mean the stream that people watch the most, everybody was complaining that the sound was not loud enough, so I try not to reproduce the same mistake. Right, so the PR I want to work on is on Julia Lang itself. So basically, a few weeks ago, I was working with sparse vectors and realized that one of the operations I was doing in an optimization function, in an optimization framework, the key bottleneck on performance was a dot product between two vectors, and it happened to be extremely expensive or inefficient when you had a sparse on one side and a dense vector on the other side, which is, let me see if we can find it. That was not a big deal. Yeah, that was this one. So I opened this PR because dot product was slow. Yeah, it was for sparse matrices on one side and dense vectors, or I assume I wanted to say dense matrices. So anyway, dense array of the same dimension. If you do a dot product between the two, you're supposed to have something that's decently efficient. And so what I did in this PR is add specialized versions of the dot product for some specific types of matrices and specific types of vectors. So here for diagonal, for example, if you have two diagonal matrices, the dot product is extremely cheap. You should just compute the dot product of the diagonals. It makes sense. If you have a diagonal and any other matrix, then you should use the dot product of the diagonal itself, because how to say that, you don't want to use the other vector. Usually I think that the diagonal matrix should prevail. The problem is, if you generalize it like this, then many types of sparse matrices will end up building their own dot product. Like, well, sparse matrix will have its own dot product, and then if you have this, you end up having method ambiguity, because if you have two generic sparse matrices, which dot product should be prioritized? Should I use the one from diagonal, or should I use the ones from my other matrix type? And that's, I guess, one key issue. The problem is the generic dot product is fairly bad, in the sense that it doesn't use any sparsity information. It uses all the indices of the matrices. And the conversation we ended up having in this PR was that we are lacking way to specify I want all of my non-zeros on a given array. For instance, I want to iterate over all the indices that are non-zeros in a matrix or in a vector on one of my arrays, and then check the same thing for the other, so as to avoid iterating over everything when you don't need to. Right, so yeah, I ended up having very specialized versions everywhere, which is okay because it's fast. At the same time, it's not that great because you end up hard-coding a lot of dot products which are, in a sense, mostly the same, just grabbing the non-zeros of your specialized type and iterating over them instead of iterating over the indices of the other container. Yeah, so that was the test. So yeah, in a sense, I mostly did sparse matrices and diagonal in linear algebra. What I want to do now is, so that was the previous PR, and the open question we had was, should we generalize this? I think the answer should be yes, and that's what I want to do today. More specifically, I want to look at this here, which is, I just started this PR and wanted to look at how to define an interface for generic sparse indices, which would be basically, so in Julia you have this function. So if I have an array, let's say a matrix, I have this function each index of A, which will return a container that has to be initerable, and I think it has to be indexable also, of all the indices of this array. So in that case, ooh, interesting. I thought this would be, I thought this would be Cartesian indices. Interesting. Anyway, so here this returns something that you can index on, in the sense that, so this is representing all the numbers 1 to 9, and indeed these are all the indices of this array. So this is a two-dimensional array, so I can do that, and this is usually what you want to do for a matrix. But you can also give it just one number, and how it will index in that case is in a column major flavor, which means it will index here, 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 then here, here, here. So it's basically storing all the columns in a contiguous manner, and so rows are detached or decomposed, you could say. Right. So that's it for each index, and the function we want to add would be something like each stored index, which will give me an iterator in the same sense as this, but not on all the indices, but just on the structural non-zero indices. So for example, if I use sparse arrays and I create a sparse vector, sp zeros of let's say 4, then my I don't have any structural non-zeros. I mean, my array knows that I don't have anything that is 0. I don't even need to check the array. The array just knows, for example, in that case I have this field nz_int, which is the non-zero indices, and this is empty. So my array can know in advance I don't have any structural non-zero. So you don't need to loop over the array for that. So more generically, there's now this sparse arrays that nz_int, nope, in type, nope. There is a function somewhere here in sparse arrays that gives you the non-zero indices, but it's not exported, and it's a bit debated on the name. nz non-zero ints, yeah, this one. So if I use this function on my array, this gives me that. The thing is, we only have this defined for sparse vectors and a sub-array t1 of 1, 2, what is that? Okay, it's a sub-array of a sparse vector. So I think if you do a slice, so this means I have it for V, and this will give me my non-zero indices. And if I do a view of V, let's say on this should work. Nope, it doesn't. Can I do that? Yes. Oh, this is dense. Interesting. No, is it? No. Let's say 1 to 3. No. Oh yeah, base 1 to something. It's weird that it's hard coded like this, but interesting. So this should be valid. No, it isn't. No method matching, yada yada. So something is not matching between this. Yeah, anyways, I don't think I should stay too long on that. Anyway, so there's this function, non-zero indices. It's not exported and people don't use it that much yet. And also it's defined in sparse arrays. That's an issue. What we want is having defined at the Julia level for a very, let's say, logistical reason. Do I have my other terminal here? Yes. Okay, we won't look at all the stdlibs. But basically we saw that in the PR we had some sparse functions we need to define for linear algebra, right? Like the diagonal matrix type. I'm gonna have way too many terminals open, sorry for that. Using linear algebra, sparse arrays. If I now do this, is it also the same in... Yes, okay. Right, so linear algebra dot diagonal of 1. Yeah. So this here is a sparse matrix with just non-zeros on the diagonal, and it's even dictated by the type where the non-zeros are. In the case of sparse arrays, you know that there are some non-zeros, and you can know them at runtime. In that case, you know them at compile time. There might be some zero on the diagonal, but this would not be some structural zeros. I just know that anything outside of my diagonal will never be something else than 0. Right. Do we have questions so far? It's 15 minutes already. Yeah, I think I said at 3:15, which is the time now, but I messed up on the link and I put 3, so people who joined on time were already here, and some people might still join now. Let me just grab my Shikori here, hydrate myself. And do people have questions in the meantime? So now that this is out of the way, we can look at what we actually want to do. A question: how do I find non-structural zeros? So for a non-structural zero, so it would be like, for example, in this matrix A, if I say A of 1, 1 equals 0, I don't have an efficient way of knowing where my 0 is for a generic matrix. So if you're past a matrix in a function and you don't have any information, you need to look at the values and check, do I have a 0, and now do I have a 0. So you could do something like so 0 indices equal, let's do with a comprehension, I for I in each index of A, if A of I, let's use is 0. So this will be exactly 0. So watch out for floating point numbers. Nope. Yeah, is 0. Better like that. So that would be how you find 0 indices in a generic way. But now if A is, let's say, a 0 matrix, but with let's say, I'm trying. Sorry about the fan noise. I think this will definitely get worse now. Maybe if we start to. And this is already a bit longer. We don't see it here, but so the 0 indices now would be everything, all the indices. And so the problem is we don't know in advance what would be the non-zeros, because we just have to look for the values. In the case of sparse matrices, ASP zeros. So this would be a sparse matrix now with this SP from for sparse and zeros for the same constructor as the zeros from dense arrays. And then I will give it a size, for example, 200 by 200. So this will also be a matrix. And I don't have anything printed here, but so it's an interesting pattern. So let's say now that AS equal, I'm not sure I can do that. Nope. I think I can do SP sparse, something like that. Nope. Yeah, I just wanted to show you. Did I instantiate? Okay, I'm going to instantiate a diagonal of, let's say, oh, can I do that? Maybe. So I here is from linear algebra, and this is the identity matrix. So zeros everywhere, ones on the diagonal. Nope. Oh yeah, you don't need to pass two integers here. Okay, so D is now a diagonal, and I'm gonna say that, so AS was my sparse matrix, and I'm gonna copy all the elements from D into AS. And now if I print AS, we see something really nice, which is you get pixels with everything in blank except where you have non-zeros. Like if I do let's say 150 equal something, then A will have, wait, oh no, yeah, A was my dense matrix. That's AS, my sparse matrix. And now if I look at AS, I have my spots that I instantiated here. So this will be the 150. And so everywhere where I have a non-zero, I have this tiny white dot, and otherwise the rest is black. So you can see your sparsity pattern directly. Okay, back to the question of how do I find non-structural zeros. Well, we saw how to look for non-structural zeros. So you just look through your array and look for zero values. And now the structural zeros, you have different way. Basically, for matrices, you have to iterate through NZ1, no, sparse arrays. There is a method somewhere to find. I think I have it on the PR somewhere. No, not yet. Okay, we're gonna see it later. But there's a method to find the sparse indices of the non-zero indices of an array, and in the case of a sparse array, this is structural. This is also in the Julia docs for sparse arrays. Right. Now that I got lost in something else, let's get back to what we want to do. So the idea here is a generic indexed, I should say, iterator for structural non-zeros of abstract arrays. The fact that we want it for abstract arrays means we can't have it in sparse arrays, because we also want it for linear algebra, and so you can't have cross dependencies between the std-libs. Sparse array depends on linear algebra, and so you can't have linear algebra depending on a function from sparse array. I hope I make sense. And so one solution would be defining this sparse index iterator in linear algebra. That would be one solution. I don't think this is the best. I think the best thing would be to have this defined in base, and we'll see what people think about it when we discuss the PR. But for now, I consider that I will have it in base. And this is what I did in our first commit here. And the second commit is implementing it for diagonal, so we can look at the changes we had up to now. I hope the screen is not too small. I might want to zoom a bit, let me know. So the first thing I did is define this each stored index function that takes my array, or I didn't add any type constraint here for a moment. So it takes an array and returns an indexed iterator or indexable iterator over the structural non-zeros of this array. And so by default, I will consider that this is called each stored index the indices where I know I have something non-zero. And by default, I will consider that all my indices are potential non-zeros. This will always be correct. So this might be inefficient in some cases, but it will always be correct in the sense that I don't want to miss on a potential non-zero. You would use this function, for example, in sum or dot product or anything like this. Basically, in a sum, you want to sum over all the elements of an array. But this is equivalent to summing over all the elements that are not zero. Except that if you only sum the elements where you know in advance it's not zero, then you can win a lot of time. Again, I hope I'm clear. And so by default, this will remain each index. And so this will be correct, but slow. Now we want to make it fast for specialized types. And the first one will be diagonal in linear algebra. So again, the diagonal matrix is a matrix with zeros everywhere except on the diagonal. And here, I also have a suggestion to apply. I would definitely add it now. And so here, this base each stored index function that I defined, implemented for a diagonal, will return the iterator over the diagonal indices of the matrix D. And then if I want to sum, then I will use this each stored index, which will give me all the non-zeros, and then sum over all these elements. So we're returning, remember, the indices here and not the elements themselves. So in the case of diagonal, this is fairly easy. In some other cases, it might be a bit trickier. I'm thinking, for example, of triangular matrices, things like this. Right. Otherwise, so this is it for diagonal, and I think the stream now will be about doing the same thing for sparse arrays. Alright, I don't have any questions in the chat. Wonderful. So the first thing I'll do, because I haven't touched this PR for a long time, I hope this is big enough. I also changed the contrasts because someone let me know the last time that my terminal colors were not that eye friendly, like some colors were not well contrasted. Alright, so I pull the latest master because Julian has moved quite a bit since the last time I touched this PR. Yeah, no surprise here. And then check out, what was my branch again? Dot index. This should not be called like this, but well. And let's merge master. Hope we don't have conflict. We don't have conflict. Wonderful. And so now we will work on implementing this each stored index for sparse arrays. So I'll go in the alright, maybe one good thing to know is first look at what is there. Oh, I don't have tree installed. Does exa have tree? Yes, I think so. Yeah. Okay, this is now a bit too big. Yeah, this is also. Do I have depth? Yes, depth equal to some. No. Do I have some? No. Ah. Oh no. Yeah. How do I print up to a given depth in exa? List here. Nope. 3. Yes, okay. I should definitely not look into it now. Okay. Anyways, right. So we can look really quickly into what we have. So this is in Julia itself. Okay, I should have really looked into it in another time. Let's just look at ls. So we have here base, which is where all the base Julia Lang code lives. So this will be in pure Julia. src will be all the wizardry stuff that I never touch, which is written in C and other things. Let me just scare myself. Alright, so we have some compiled objects. This is some C, some C++, a bit of it. We also have some scheme here. So basically this is where the super small core, the smallest core of Julia is. And base is where most of the Julia code lives. And so in base you will have things that are in pure Julia, and most of what you actually use is in there. So that's fairly useful because to contribute to Julia you just have to know Julia code, which is super useful. Oh, hi there, I didn't see the Julia Lang account is here. Nice to see you all. So right, so this is base, and so this is where we implemented our function. So if I go in base and I look for my each stored index, where did I put it? In abstract array, which makes sense. I think I just put it next to each index, which is the other function for this. Right, so and this is the only modification we're going to do on base. And then most of the work for this PR will be in the standard libraries. So in that case we have a bunch of them, but we'll be mostly interested in linear algebra, which is here. Right, make it a bit bigger. I hope this is not too hard on the eyes. Right, so we said linear algebra, which is here, which is defining a bunch of vectors, matrices, mostly matrices, I think, special matrices, and functions on them. So that's one thing. And the other one we'll be interested in is sparse arrays, which is defining, well, a sparse array interface. I think this is still an ongoing work, how to define a generic sparse array interface. And also, and I guess this PR is a bit part of thinking on how to define a generic sparse array interface, and also defining some specific sparse matrix types and sparse vector types. Right, and so I guess the crux of the work will now be in sparse array itself for now. And the nice thing is, so all the standard libraries, or I think most of them at least, are defined and behave just as normal Julia packages. So they have a project toml, which is just like you would have in any normal Julia project in your own. They have source, test, and docs. And so the cool thing is, if you have a version of Julia installed and you just want to do modifications on, let's say, sparse arrays, you can modify it, and then import it normally as if it was a normal project, even though it's a standard lib. So that's great. You don't need to recompile Julia to test some of the things you added to sparse arrays, for example. All right, enough talking, I think, and time to get some work done. All right, so where are we gonna add this? I guess the nice thing to add would be first sparse vector, because this is an easy one, and because sparse vector already has this function we talked about a second before that I already forgot, which is this one, non-zero ins. And so here we see non-zero ins is defined on sparse vectors and sparse vector view, which is this alias for another type. And I think the goal was to deprecate at some point non-zero ins. with some other name, which is the one we suggested here. So the name we suggested for this PR is not mine. This was the result of thoughts on and discussions on another PR about how to rename things in the sparse array interface. Right, so in that case, I will just lazily I'll add that non-zero inst for sparse vector, add that here, and this would be based on each stored index, which is my predefined function, or my function defined in base, and I will define it for sparse vector first, and this would be get field and z ins, and this is perfect because I don't have to do anything here. I could also do it for a sparse column view. This would make sense, I think. Yeah, let's see. I'm not sure. For now, I guess it would make sense to just define it for top level types, and this looks like an alias or something you would use internally, not so much something you would import. Like you wouldn't wake up a day and say, oh, let's use sparse column view. You would use a sparse matrix, and then this one will have internally sparse column views, I guess. Alright, so this, well, I guess this is it for this one. Yeah. So what would be a good test for that? Let's just add tests right now, so we don't forget anything. So again, this is a plain Julia package, which means you can add tests, and the tests are all just like you would have in your normal packages. That's great. Module sparse vector tests. Okay, this is importing other non-zero ends. Include forbidden properties. Ooh, that sounds like the dark arts. I'm not going to touch that. Okay, so this is constructing a sparse vector of size 8. It has these non-zero indices and these non-zero values. So this would be a sparse vector of element type float and of index type integer. Yes, exactly here. Basic property, and I guess we can just test it here. This would be a bit of a dumb test now, because we basically copied the implementation, so no surprise. Each stored index. Alright. Non-zeros. Okay. And we can also add a test that non-zeros is equal to. So the non-zeros are the values, the structural non-zeros of the values, and each stored index returns the indices of these non-zeros. So it means, in general, a good test that you could add for any sparse array is that x indexed at these each stored indices, or each stored index has to be the non-zeros. Right. And I think that's it for now. This is our first test. Do we have questions so far? I might go a bit fast or a bit too slow because I'm also thinking this through and haven't prepared anything. I just wanted to come and build this PR from scratch, even though I already cheated with one commit a few weeks ago. So if you're a beginner in Julia, you don't know what I'm doing, or if you're advanced in Julia and you don't know what I'm doing, this is also possible, because I don't know exactly myself. Feel free to ask any question. If the sound is not good, also feel free to let me know. This will be helpful. So yeah, if any beginner question is definitely welcome, and I can definitely make some asides while it's on the topic. I don't think I'm gonna change anything here. This doesn't sound like something that would be useful. Conversion to dense array, no. No, this is definitely not useful for now to change it. Alright, so how am I No. Interesting. How am I gonna test this? I was about to say we could just try it out, but the subtlety here is I changed base, and I added a function to base. And I cannot just come up with, I can't, with my current Julia version, say, well, please try this out, because, well, this will fail. Or actually we can, I can use Julia 1.6 here and activate the Sparse project. So as we see, this is, I'm now in this, and I can test. And this will fail, because it will tell me, hey, what is this base dot each stored index function you're talking about? I don't have this. And we don't have it because I'm using Julia 1.6, which I installed on my, or downloaded on my machine, which is not the same as this Julia source that I now have. What I can do on the side is, and this is gonna make some fan noise, sorry again for the background noise, my laptop will go bananas. But what we can do now is make Julia on the side, so compile this version of Julia here with my modification made, so that the binary we obtain can be used to actually test our sparse array modifications. So the tests that are running now are the one from sparse arrays. And again, this is great because I can modify the standard lib without actually rebuilding Julia itself or modifying Julia itself. So standard lib being plain Julia packages really has some great advantage. Alright, so while we're at it, I don't think I have much more to do here. The tricky part will definitely be building this for some other more esoteric array types, and also for sparse matrices, because the sparse matrix interface might be a bit trickier to get. Yeah, one thing I might want to check is what is, so yeah, this is going to compile everything. So you see here, this is actually compiling the SRC part of Julia. So this is compiling the C and C++ part of Julia, the scheme part, and so on. I think these fun fact, these SKMs, these things here, I'm not even sure it's a standard language, but it might be a tiny language built by Jeff Bezanson, who was one of the co-creators of Julia, I think. If someone in the chat can confirm it, I'm interested. Let's see what it looks like. Yeah, it's definitely some strong Lisp flavor, but I am not familiar enough with Lisp to know what flavor of Lisp it looks or feels like. Interesting. That's something else. Alright, enough scheme for today. Yeah, I think this is interesting. Package printf not found in current path. Well, this is so it seems like sparse arrays needs printf but doesn't have it in its dependencies. What thing I could do is add printf here, although I'm not sure if it's needed for the dependencies or for the direct dependencies of sparse arrays, or if it's needed for the test dependencies. So I'm gonna go in lib sparse arrays and look for, I assume this would be for printf, and this is only used in the test, so what I could do is add it in the test only. I'm not sure what's the UID of printf, so I'll just just add it like this. So one bother I have sometimes is I want to add printf to the test dependencies from the REPL directly, and this will add it to the main dependencies of sparse arrays. So we'll see that in the project toml now. Yes, this added printf here, but we want it actually in the extras there. So I'll just move it like this and then add it to my to my targets test. But what I would like is is the possibility to add something from the REPL directly in my test. So if anyone listening is willing to do a PR for that, I'd be really interested. Someone mentions in the chat, I think since version 1.5 or something, Julia supports a project toml in tests, and this is exact, yes. It does support a version of project toml in test, although I'm not sure we will have it in base Julia itself. That's an interesting question. No, base Julia, I'm not sure base Julia uses it for now. I'm not sure any of the standard libraries do have a project toml. I don't think so. Also, I've rarely used it because many of the packages I work on do require or try to require 1.0 compatibility, and because of that they cannot use this feature of project toml in test. Otherwise there could be some out of sync between the two. But otherwise I agree, not having an easy way to interact with your test environment is sometimes a big source of frustration. Alright, so where are we now? Makes sense, I dropped 1.0 a while ago. Yes, this is definitely something I would have liked to do on some packages. Yeah, not looking at jump. Alright, so I added Printf, so it should now be happy about it. So let us try. So I rerun the test for sparse arrays now that Printf is incorporated in the test dependencies, and we'll see what it gives. So it does seem to be happier, but I think it was happy up to now, at least. It was happy up to Extrema, so we still have a bit of time. In the meantime, yeah, my Julia compilation is going okay, slowly but okay. Right, what else do we want to do? Yeah, so we implemented this each stored index for sparse arrays, but we would like it for sparse matrices, and this is where it could get tricky. Alright. Docs Julilang. No, I want the latest, I think. Yes. Ooh. Work in progress, yes. But I do want the bleeding edge because I mean this 1.7 dev is like the nightly, I think, either nightly or master, and this is what I'm developing on, so it makes sense to look at this documentation when contributing to Julia itself, even though usually when you're working you would be working with the stable version, which would be in that case 1.5, so the latest stable, or if you like bleeding edge, then 1.6.rc-rc, which would be the release candidate for the next stable release version of Julia. Alright, I wanted to look at sparse arrays, yes. So this is the official Julia docs. Oops, again, sorry, I think this might be a bit small. Just always let me know whenever I forget to zoom in. And let's see, so this is the base sparse matrix and the one we want to work on. And we want to get an iterator over the non-zero indices of this. And what I have here is sparse vector. So that's the constructor, okay. Operations. Correspondence, no. This will not have a correspondence in dense matrices. So I'm looking for given functions that allow one to iterate over the indices of a sparse matrix without iterating over all the indices of a matrix. Like if it's a n by m, I don't want to iterate over all the n by m. Is sparse number of non-zeros, so we're getting close here. Find non-zeros, that's it, yes, exactly. Returns a tuple ijv where I and j are the row and column indices of a stored, structurally non-zero values. Yes, exactly that. So yeah, this will return all the rows, all the columns, and all the values. Yes, perfect. Okay, and what we want now is I'm trying to think of a way to do this in a non-allocating manner. Because we want to have an iterator over the pairs 1, 1, 1, 2, 3, 2, and 2, 3, without allocating a new vector on that. So this find non-zeros is non-allocating, it's just returning a view of the indices. And this is great because this means getting indices should be cheap in general. So how could we do that? We could use kind of zip vector, but I don't think there's any zip vector in base. Just to give you an idea of what I'd like to have now. A zip vector would be a structure, zip vector. That would be an abstract vector of something, or in that case of tuple, let's say for now of tuple t1, t2, and this will actually have inside a first vector, which would be a vector, let's say a plain vector for now of t1, and the second one that would be a plain vector of v2. And what it actually does is every time you index, so if you have a zv that's a zip vector, every time you index into it at say index 3, what it will return is the tuple of v1 at 3 and v2 at 3. So if you have done a bit of Julia, you know that there is zip that does that. Except zip takes iterators and returns itself an iterator. So if I have 1, 5, and then 2, 6, and I zip them, 1, 5, 2, 6, so I get a new iterator, so let's call it ZV. This is of type zip something, base iterator zip, tuple unit range, okay. And so I can iterate over it for I in ZV, println I. Okay, and this gives me tuples, so this is fine. What I want now is the same thing, but with as an array. And the problem is I cannot index into it, I think. Yes, exactly. No method get index, iterator zip, and this is sad. Actually, I think this should just be defined on iterator zip. And I also don't have a length for it. Oh, I do, sorry. Where? This is funny that I do have a length for this. Zip min length. Okay, so this is getting the smallest length of all the elements and then returning the length. Okay, well actually then this makes sense. I mean, in that case it would make sense for a zip to also have get index in some sense. And then this means that we could have a an iterator that works for our purpose and that still behaves like an array. So yeah, zip could work. The second thing is we actually don't want tuples because we can't index a matrix. So we can't index a matrix with tuples, like this will not work. What we want is indices itself, so this will do like, this will be the equivalent of 1, 2, which is okay, or we can have Cartesian index. This will work, yes. So I think we do need a specialized type here. I'm not sure I'm thrilled about that. Well, we'll see. Well, aside apart, let's get back to what we wanted to do. So we wanted to have an index iterator for the non-zero indices, which is the Cartesian indices built from that. Well, actually we could just have it allocate and be okay with it. That would be one solution. And this would be the smallest change, and then require people to add a get index on zip if we want to have something correct, or something non-allocating and cheaper. Alright, so let's do this. So this would be for any, this will work for any sparse matrices, I think. Abstract sparse matrices. Yeah, I think this is okay for abstract sparse matrix. Alright. Oh, error during testing. Wait, we did add printf. What do you want? Where is this? Interesting. Yeah, we do have printf added to the package. It's odd that it's not accepting it. I mean, we did. Well, okay, let's just leave it for now. Alright, well, you know what? Let's just add it and see if our tests pass. Okay. Okay, cool. I could also compile Julia here. So I'm on 1.7, and I could now do this, and then each stored index. So this is now the compiled version of my the compiled version of my Julia repository, or the local one. Yeah, and this is defaulting now to each index. So this is getting to the default one. And if I now have a diagonal matrix, oops, I didn't import linear algebra. And let's see now which version gets called for base.each stored index of D. Okay, and this is this one. Oh, yeah, we'll see later what's wrong here. Right. And so this is a cheap iterator over all the non-zero indices, which is exactly the diagonal of my matrix. And so if I do D of this, I will get just all ones. Yes, exactly. The bother I have here is that this is, yeah, well, this shouldn't be a sparse array because this is dense. Which one gets called here? Get index abstract array eyes. Interesting. So what bothers me here is that this operation returns a sparse vector, but this sparse vector is actually super dense. Like, it's 100% dense, literally, because this is just all ones. So I'm not sure this is that smart to have get index on D with a range or a bunch of indices, return something that's sparse. Anyways, this is not this PR. One thing I'm trying to maintain now in open source contributions is a scope on each PR, meaning if I know I want to contribute something, then I will try not to deviate too much from that. For example, we will not implement a zip vector here. We will not change this, because otherwise the PR gets messy, it wastes everybody's time and so on. So yeah, we'll try to stay as minimalist as possible in the set of changes we do. And this is not something I've always done in the past and learned it the hard way. Or have I learned it? I'm not sure. Alright, so sparse, so we now want to go on with sparse matrix. Alright, so this is the main structure of the sparse matrix, column storage, compressed column storage, compressed storage column, compress sparse column data structure. Okay, yeah. Should just read things sometimes. Alright, so, and I wanted to look for the find NZ function. Ooh, interesting. Find NZ is allocating. I didn't think so. So it is, if you see, like, so this find non-zeros is allocating a vector of i's, of j's, and the values, and then allocating it. This is I thought this was just a view on it. Well, till. Which is a bit of a bother, but at the same time it means that returning iterators over indices might also be okay to allocate. So we can have something that allocates for that, which is in some sense great. So base that each stored index of this above will be, so this would be the same thing as that. Oops. Function. And so this will, yeah, we'll just be lazy and call that, or we could just we could also copy it, because we don't need to store the vectors. So this will be one less allocation. Yep, we might actually be smarter returning this like that. Okay, so here we are, except we don't need the v's because we just want the values. And we might actually want to yes, and what we want to do is return just one vector of Cartesian indices. Cartesian index in that case. And I have to see what's the type parameter for a Cartesian index. If I just type int like this, Cartesian index sometimes produced by each index, yada yada. Yeah, okay, not helping. So I don't have a second parameter here. No. Okay, so it's just Cartesian index of ti. It makes sense. So this is the integer type for the matrix with a number of non-zeros. I don't need j either. Ooh, wait, no. This has to be what is returned by each index on the sparse matrix? Hi, I just tuned in. Are you working on a specific package or on the general Julia repo? I'm working on the Julia repo this time. So specifically, I'm working on the mostly on sparse arrays, on the sparse arrays standard library, and a bit on linear algebra, but I'm mostly trying to work on the sparse array interface in general, and in that case adding one function to base Julia, which will be each stored index, which will return an iterator, an indexed iterator over all the structural non-zero indices of a given array or collection. So yeah, that's it. And for now, I wouldn't say struggling, we've seen worse, but yeah, going well. So I'm now implementing this each stored index for sparse matrices, if we can. And I'm trying to find Cartesian index. Let's remain focused. Let's say M is a sparse zeros of 200, 200, or 100. Oops. What does this return? Each index of M. Yes, okay. Cartesian indices 2 tuple. Okay. Okay. So this is all the indices. Oh no. Yeah. So I is already a value here, which is linear algebra I. I shouldn't use it as a verbal name. Indices. And what is indices of 1 now? And what is its type? Cartesian index 2. Okay, interesting. Oh yeah, okay. So this has to have the dimension here. Cartesian index 2. Can I create it like this? This is. Can I do that? Yeah, with let's say num and z equal 4. Yeah, it seems to work. Okay. Alright, so this is just giving me garbage data here, which is fine. Alright, and then so this doesn't change. And then indices of count will be so this would be the row value first and the column value second. The Cartesian index, row value, and then column, and that's it. And then I just return, in that case, indices. Ooh, I think you have some. Oh no, okay. Okay. Yeah, one more. Less space. This looks decent. Or in which version of Julia am I now? Where am I? Here. Okay. So I now load the version of Julia where I do have this each stored index defined, and I'm going to import linear algebra and import sparse arrays, and then I will just copy paste bluntly my function here using sparse arrays. Alright, I do need sparse arrays. So if I was not in Julia base here, what I'm doing would be called type piracy, which is when you implement a function you didn't define for a type you didn't define either. This means you would change behavior of existing code by defining this function. And overall this is to be avoided because this creates unpredictable behavior. Like you don't have your package, you do something unrelated to your package, and then you load your package and you do it again and it changes behavior, which is bad. Alright, and so that's why you would normally avoid it. In that case, I'm just doing this because I want to test out if this works before actually running my tests or committing or anything. Right, so let me create a sp0, so a sparse matrix, and now base.each stored index on this sparse matrix. Get call ptr not defined. Oh right, yeah, I do need so all these functions that are not exported by sparse arrays, I need to specify them explicitly, like this. Whoop. Get call ptr, and I think row vals might be unexported. Okay, and I don't have any stored index, which makes sense because my matrix is empty. Now, if I add elements, let's say we add pi. Okay, this seems to work decently up to now. Let's add some more tricky cases. Well, tricky. 33. That sounds good. And so my definition is that if I do m of all these base each stored index, this is supposed to give me all the non-zero values. And that's the case. NNZ of m. So NNZ stands for non-zero. Yeah, non-zeros. Oh no, that's the number of non-zeros. I want non-zeros. Oh, non-zeros might work. No, of m. Oh yeah, and it's exactly the same, because so non-zeros is returning me the values, the non-zero values of my array. Well, that seems to work. This is great. I wasn't expecting it to work that fast, to be honest. So this is already a victory. Now the question is, can we make it better for, so we have it for abstract sparse matrix CSC. Could we use it for abstract sparse matrix itself? And I would say no. Yes, I would say no, because we need to use this column pointer machinery here, which is specific to sparse matrix pointers. To sparse matrices CSC, sorry. Alright, so I would say this is working. Outside of the test, of course. Well, I still don't get why the test wouldn't work now. Anyway, so the real way to run the test locally will be, so I used make to build my project. What I would actually need is use make test, but which is going to take forever. So for now, I'll just try to do it the hacky way, which is what we're all here for. Alright, tests. So we implemented it for sparse vectors, we added a test. Now we implemented it for sparse matrices, we need tests. Made sparse, well, why is the sparse simple matrix? Why is it called simple matrix? Wait, is this sparse array? What is that? Am I in the source, or is this? I'm not sure what this is for. Sparse. Why do we have this simple S matrix in sparse arrays? I'm not sure what this is doing here. Interesting. Anyway, this is not what we're looking for. We're looking for, let's say, sparse. I think this might be that. Nope. Micro. Sparse tests. Oh yeah, show with bright patterns is what we saw at the beginning. So showing the non-zero pattern of sparse matrices in the terminal in this nice way in the REPL. Oh yeah, so this simple S matrix might be used for utils in general, I think. Interesting. Okay. Is sparse, so we're basically looking for non-zero indices, wherever this is test. Here, okay. So whatever this is here, we can add a test for base.each stored index. This has to be 3. This has to be 1, 3. Okay, and then non-zeros is this, and we can. Oh, this is interesting. In link to the question Paul asked. You saw here we have a test that the non-zeros are actually zeros, which may sound a bit odd, but the difference is, so these are structural non-zeros, which means we don't know in advance that they will be that their value will be equal to 0. We have a value stored, it just happens to be 0, but when the value is not stored, by default it would be assumed to be 0. So these are zeros that are non-structural because these are actually stored values. You have a way to remove these. So for example, if you have a sparse matrix and you accidentally store a lot of zeros, so you do store them actively in there, you have a way to avoid keeping them, because some operations will become less efficient as you have more data, and so you have a way to clean this up, which is drop zeros. Yes, drop zeros. So you will have your drop zeros of your array. This will return you a new sparse array where all the zeros have been removed, and you have drop zeros in place like this, which will remove all the zeros from your array. So if we look at, I defined M, right? So M here is my sparse matrix with just 2 entries, 2 stored entries, and I can say M of let's say 3 is equal to 0.0, and now M has, oh no, just 2, it just ignored it. Okay, now I stored something, so M now has 3 entries, and now what I can do is, I guess, minus equal 1. If I do that, yes, I have now 3 entries. My third entry is at 3, and it's 0, so I won. I now have an entry that is 0, but it's not considered a structural 0. And so if I do drop zeros on this, I now removed one of these entries. I just have 2 of them instead of 3. Alright. Great. Oh, one question, and the function you are working on is exactly what I was missing. I also need the indices in my case. So if you have, so that's great. First, I think many people are missing this function, and there was a lot of discussion way before me on how to best make this. I'm not sure if what I'm proposing here will be the best solution or the one that's retained, but I think this is at least adding to the conversation. So one good test here for this drop non-zeros would be drop zeros on V and then test that the non-zeros is empty. But we're not going to do that now. I'll just add one test here that V on each stored index of V has to be equal to the non-zeros of V, and this has to be the case all the time. Alright. Would there be some better or some other ways to do that, or some other tests we could add? For now I don't see much. I guess the next thing to do will be move on to the linear algebra matrix types. If you don't have any questions in the meantime. I don't think there's much more to test here. Alright, I guess we can just commit for now. We modified things. Yeah, I don't think I will commit the project toml. I will just add the source and the tests. So this will be implement each stored index for sparse vex mats, Ooh, and I don't think I will be able to push here because I didn't pull the latest. Yes, exactly. Okay. And what I didn't pull was a suggestion that was made by a reviewer of a pull request who's done an amazing work also reviewing the other one. I do want to give him credit here. Yes, Daniel looked at the PR and also already made a suggestion here to use directly another function for diagonal. And so yeah. So we now have all these files changed because we added a bunch of pull requests. All right. So yes, we said the next thing was moving to linear algebra, and we do have a lot of functions here. And so what I might want to do in that case is look at my previous PR, which I'm not sure where I put it. Oh yeah, so you see this is linked to the previous discussion saying export non-zero indices, and then people were saying it would be better to have another name, which would be in that case each stored index, I think. Right, so I first added this issue because I had a problem with this being slow, and then the initial PR was this one. Yes, okay. So this was the last PR, faster dot product for sparse matrices and dense vectors. Okay, and then so yeah, what I wanted to look at is what did I change? Which matrix types did I implement? So diagonal for sure, but this is already made. Or the this is interesting. How do we represent the sparse zeros of an adjoint or a transpose? Or for now, I'm gonna think in simply in terms of reals, then it's gonna be the transpose of a matrix. So if you have all the non-zeros, you don't want to revert all the indices yourself, I think. You might want to do that lazily. I'm not sure there would be a function for that. Interesting. Yeah, this is a bit of an open question. We might want to do it eagerly, so that means you get the non-zeros, the non-zero indices of a parent array, and then you transpose that Cartesian index. Yeah, might be a solution. It's eager, so it needs reallocating, but it might be the simplest way. Question: will you be presenting on the upcoming Julicon? Or maybe, I mean, I submitted something, a light talk. I didn't submit a big one for now, but we still have up to the end of the month, so still 10 days to submit. So I encourage anyone here to submit some proposal if they have some ideas, even something light. In my case, I'm presenting something super tiny. It's just an interesting topic to bring on, even though it's not revolutionizing anything. So yeah, if you have open small topics, feel free to present. Everybody is welcome to present their ideas there. It's not you don't have to have contributed to Julia, or you don't have to have you don't have to have done hours and hours of streaming or tens of open source packages. Really, anyone can present very interesting ideas, even some work done in Julia and not open source all the time. So yeah, feel free to do it. So you submitted already? Yes, I did submit because I wasn't sure if I would extend the call for proposal for the first time, so I was a bit like, yeah, let's be safe. So I have something. Yeah, I was thinking of having another work presented, but I'm still thinking about it. Yeah, so if you do find the time to write an abstract, definitely do it. You can also contact the Julicon team to get some information if you're not sure. And there is also, okay, yeah, I guess I can take a few minutes for that because this is definitely worth it. Julicon.org. There is also a track called Experience. I'm not sure if we're going to talk about it here. Submit a proposal. Experience, yes, here. There's also this track called Experiences for new Julia developers or people that are new to Julia in general. And this is for, well, giving your feedback or giving your impression or your first experience using Julia. So you definitely don't need to be a Julia expert. You don't need to have something specific for Julia programmers or anything. You just need to have your point of view on that. And so this would be like a flash talk on, well, this is why I got into it and why I'm using it now. Alright. Back to our back to our I'm gonna manage to say it. Back to our stored indices. But I actually might want to take a break or refill my hot drink because I'm running low and also the bottom of my cup is getting cold. So yeah, I'll drop there for 5 minutes and we'll see you in roughly 5. Alright, I'm gonna cut the stream for now and yeah, see you. Alright, let's get back to it. Do you all see? Yes, it is working. Sounds still good, I hope. Alright, so we left on linear algebra, which might be a bit trickier to get, but definitely also more interesting, because I think lots of functions, lots of computation heavy functions will use some parts of linear algebra at least. This is a very hand wavy statement, but I think this might make sense. Let me just grab my cup. So the open question was on which matrix types, or on which array types in general, do we want to implement each stored index in a specialized way, I imply. First thing is, I wonder if there's some other, let's see, subtypes of abstract vector specifically. What is there for one-dimensional vector? Range is definitely dense. Abstract sparse vector, we might want to... No. This is dense, I think. Reshaped. Reshaped is interesting. Yeah, some people might want to implement it later. Range is... is range dense? Yes, range is dense. Yeah. Bit array is dense, definitely. Linear indices is dense. Well, duh. Permuted dims is dense. Oh yeah, this is the tricky one. Subarray. This is one of the tricky ones, at least. And also, I realized I forgot to load linear algebra. I think there might be some more. No, okay. So why is subarray specifically tricky? Because a subarray will be sparse only if the supertype is itself sparse. Yeah. What is each index of? Yeah, this gets tricky, because so a subarray is giving you a view on an existing array. So if I have micro, let's say 1, okay, this is really irregular, sorry. So let's say this is my vector here. Can everyone see it correctly? A view might give you, for example, just 2, 3 here, like a view on the second and third elements, which is all good and well, except that if you have something sparse here, you might want to actually give all the indices of the view you got. It's not trivial to me to say you should get this or that. Like you should get a customized iterator for a view. I don't know. Yeah, it might be something. I mean, the goal of this PR is to kick things off, but I might not be the best person, or I'm definitely not the best person to implement some of the interface for the array type. The goal here is to have the interface clear enough and some specifics well ironed out, so that other people can implement each stored index for their own type. Right. So in that case, yeah, we might want to do, actually not in linear algebra but in sparse array again, we might want to do transpose and adjoint for sparse matrices. One question in the chat. One thing I miss a lot in Julia is knowing when things are allocated on the stack and when on the heap. I wish this was documented for every function. It's a very good point, and the problem is this will not be documented at the function level. This should be documented by types, and I think this is mostly documented by types. If you are looking at, for example, static arrays, this might be worth arrays. No. Let's see. So if you look at static arrays, for example, this is implemented on the stack, and I think this is mentioned here. No. But yeah, basically they are implemented on the stack. And I think this is up to the types and not up to the functions to define if things get allocated on the stack or in the heap. And the tricky thing is which type you get in output is depends on which type you have in input in a non-trivial way. Even sometimes which value you have in input. Sorry for that. So I don't think you can document it at the function level. You need to document it at the type, at the level of types. And this is mostly done, I think, like here. But it might not be done in some cases. But yeah, the thing is, functions don't control what type of object gets generated. They are fully generic. But I hope this makes sense. Right, so here I do have adjoint and transpose. That's the big one I want to implement. And I want to implement them in sparse arrays. So sparse arrays depends on linear algebra, so this will fix my problem. So where do I actually manipulate adjoint, if I even do? Nope. Ooh, a lot. Oh yeah, I do have this one here. Sparse vector 1064. So what am I using this for? A definition similar to a third exists in base, but yeah. Okay. So a sparse arrays underscore is a sparse vector, or a sparse matrix CSC, or an adjoint sparse vector, or a transpose sparse vector. Interesting. Oh, because I think transposing an abstract matrix CSC is also giving you a sparse matrix. Adjoint, so what's the type of this? Adjoint of, okay, this is not helping. I thought this would return me a sparse matrix also. And what about transpose? They're also giving me a transpose. Okay, interesting. Alright, so I might want to do it in a very non-elegant way. Yeah, I fear the worst. Where did I implement this? Each stored for. Ooh, and if I have v being a sparse vector, let's say 20, what's the type of this? Adjoint of a sparse vector. And what if I transpose it? Transpose of float and sparse vector. Okay, interesting. was wondering if it was actually giving me a matrix type or something else, or something more specialized, but no, I think it might be bound or documented to always give you a transpose type or an adjoint type, even though you could give something else. Alright, SRC sparse matrix 1528. I have too many tabs open. Well, let's open another one. 1528, we said. Yes. So and I might want to give the definition now for abstract sparse matrix. So this would be for adjoint and transpose union of adjoint, so T ST, and so same thing with transpose. So this is closing the union, where we don't need TI, where TV and ST is a subtype of abstract sparse matrix CSC of TV, and we don't need that. Okay. So this will give me the stored indices for the stored indices for the adjoint or the transpose of a sparse matrix. Okay, and this would basically be the same function. I don't see a better way to do it without reallocating everything, except we reverse the row val and the column. Okay, and that's it. This is awful to do it twice like this, but I don't have a better way for now. So maybe someone will point it out in the PR. Hey, this sounds a bit odd, you should do it like this. Alright, and in the case of a symmetric, actually for any of the wrappers, so meaning of a symmetric of this, or an what's the type of abstract triangular? No, not here. Triangular. Did I load linear algebra here? Nope. This is not exported. Abstract triangular. Yes, here we are. What's the behavior? We don't have documentation for that. Well, this is sad. So I want to see if I can implement something just for abstract triangular and not for the rest of it. Subtypes of this. Let's see. Lower triangular, unit upper, yada yada. Okay. Alright, so if I do a lower triangular of my matrix M, M2 equal M of 1 to 100 and 1 to 100, and then lower triangular of M2. What's the type of this? Lower triangular of the element type and then my matrix type. Okay. Now if I do symmetric, of element type, matrix type, And I'd like to see if abstract triangular, oh yeah, okay, abstract triangular has the element type and the matrix type also, so this is perfect. Right, so in that case, so we can have, this will act, I think there's a mechanism in typed languages, like statically typed languages. I think this might be hierarchy type, where you say, I want a union of, or I want, well, I'm definitely getting out of hand here. I want a matrix type with parameter T and S. So I don't know what this M is, but it has to be parameterized by T and S in some way. And then I constrain where T and S is something, and so on. So we don't have this in Julia. So this means I need this union to explicitly say symmetric. Or I could just remove the TV here, because this is getting too long. Help your children remove TVs. Yes. Right. So this would be for any wrapper type that preserves the non-zero indices. So that would be symmetric, or that would be abstract triangular, and this is algebra abstract triangular. I think there are other ones. Well, I can just check the pull request. I think Hermitian also works the same way. Well, all of these exotic ones work the same way. Subarray doesn't, so I shouldn't touch this. But abstract triangular and these folks should work. Yes. I'm not even sure what a Hessenberg matrix is. This sounds like something physicists will use. I'm not sure what it is exactly. I did the PR using this upper Hessenberg matrix before. We are all doomed. I also remove TV. ST. Upper Hessenberg, symmetric, Hermitian. TST. Where TST. So in that case, the nice thing is we have this generic function parent, I think. Parent, yes. And this is for the parent array, exactly, of an array. Perfect. And in that case, so we can just return base each stored index of parent of S, because this will have the same non-zero indices. Wonderful. All nice and clean, and this also needs some tests. And I think once we have this tested, this should be good for a first review, or at least first opinions of people. I don't want to get too much work done before people start voicing on that, because we might have someone from the Jira contributors saying, well, actually we don't need that, or actually we shouldn't use it that way, or actually there's something better already planned, or this is incompatible with this or that. This might happen, and because of this, we might want to just not merge this PR. So in that case, better keep our energy and time for other productive things, and not lose too much on this. But I still think this is worthwhile. This is worthwhile, and this is worth having in some way. Maybe not this one, but having in some form in Julia. And so yeah, we'll see what people would be saying. But I'm excited to see what will be going on. So the last part will be adding some tests to that. So that was test sparse, yes. Well, let's see if where we have a joint use. Okay, this is not that. Wrapper of sparse, yes, I think we can do this here. What is do? Oh, do wrap. Okay, do wrap must be wrapping the matrix. So in our case, we want something. So we want another test. We want first for sparse each stored index. So each stored index of WR for WR in so the triangular, yes, but we want also so upper triangular, lower. We also want permission. Well, let's be fancy. Hermitian lower also. Let's add the two symmetric. And I think this is it. So that's the wrapper types that will not change my my stored indices. So I should definitely test for these. So s equal do wrap, and this is giving a and the wrapper, no, the wrapper and a, and then I have to test that. How can I test that? I'm not sure I will have non-zeros implemented on this. Well, I can test that the sum over each stored index. Oops. So of s at all the each stored indices of s is equal to the sum over s itself. Oops, sum, yes. Okay. So I think this is a decent enough test for now. Yeah, I might want to approximate this. No, I shouldn't approximate this. This should be exactly equal. And also because at some point this might use the efficient way, which is stored indices, and so we might want to say that this is also equal to sum of matrix of it. So this will turn S into a dense matrix. So this will remove the wrapper and remove the sparse type, or convert this to a dense matrix, and then the sum should be equal. Okay, and so we did that for the non-transforming wrapper types, and then let's do this for the transforming wrapper types. oh well, actually I can even, it does make sense to even add them here. Yeah, let's just add them here. And so this will test that, I mean, because this should be the case in any way. Right. And I think this is good for now. I'm fairly satisfied with having this additional test here. We might want to add some more afterwards, but I don't think I will do that in the stream, because I mean this would be getting a bit repetitive for now, and we've been at it for 2 hours. I think this was my rough target. So yeah, we'll be leaving this as is, I think, soon. Just commit everything, push, and then let people comment on it. What was the change in source again? Yeah, adding stored indices for everything here. I just close this. No. No, I mean Julia now. What I want to do first is launch Julia, the binary that I compiled before, and then include stdlibs sparse arrays src sparse arrays. I think this should work. Yes, okay. And now I do have my different method, well, my different method defined for each node by stored index. Yes, I do have it for sparse vector, these, so that's in sparse a matrix. Okay, cool. Alright. So this means I can now commit implemented for wrapper on sparse matrices. Alright, and I think this will now be good for review. Of course, I also wait for, well, I also see if if the CI passes, which might sometimes be tricky. But yeah, otherwise we'll see what's the feedback on that. I think the key thing here is the design, and what's the feedback on it, and should we change something, or is this just not receivable? Alright, so yeah, I hope this was enjoyable. I hope the sound was good enough and that I wasn't too confusing or going too much all over the place. If that's the case, just let me know, or let me know if you enjoyed watching this. Always eager to get feedback on that. And yeah, otherwise I wish you all a good Sunday. Enjoy the rest of it, or the beginning of it, depending on where you are. Right, and yeah, see you everyone, and take care.